Hi, welcome to the first video of the Linear Algebra Bootcamp, which is just a 90-minute review of the primer material that was available and is still available online. Linear algebra is the study of functions, surfaces, spaces that don't bend or curve. This means that it involves only scalar multiplication and addition. So this is arithmetic in higher dimensions. To represent objects in higher dimensions, we use matrices and vectors. These are just arrays or lists of numbers. They're indexed first by their row and then by their column. It's important to know that matrices and vectors in all mathematical notation will be written in bold-faced print. When we talk about the dimensions of a matrix or vector, that's also referred to first by the row and then by the column. So a 3x4 matrix has 3 rows and 4 columns. By default, when we think about a vector, we think about a column vector, which would be an n×1 vector, having 1 column and n rows. So when we look at Xij, that capital X, always a capital letter, always refers to a matrix, and the ij subscripts refer to the ijth element. So in row I, column j, the lowercase bold letters represent vectors. So here I have an example of a matrix and a vector. So x2, 3 would be that element 6 in the second row, third column. And of course, I only need one subscript for a vector because there will only be one column or row. So v2 would be the second element in the vector. Now, geometrically, something that will be important for us to think about is that there's this interchangeability between the concept of a vector and a point. Typically, when you first talk about vectors, you might have done so in physics, you talk about how they have both a direction and a magnitude. So when I write this vector A, that's the vector 1, 2. It can be thought of as that point, that red point, but also as this direction arrow that points from the origin to the corresponding point. The magnitude is the length of that arrow. So if we want the magnitude of the vector A, it's actually going to be the square root of 1 squared plus 2 squared. That's because of the Pythagorean theorem. We'll get a little bit more into that. That's actually the norm of the vector, and we'll talk about that at the end of this 90-minute primer. Let's go on and just briefly review the initial steps of matrix arithmetic. Again, this is multi-dimensional math. And we'll first cover addition and scalar multiplication, and in the next video, we'll get into matrix multiplication. Addition can only happen between two matrices that have the same size. If two matrices have the same size, then they can be added together. And in order to do so, we just add the corresponding elements. Mathematically, we might write this as the ijth element of the sum is equal to the sum of the ijth element of each matrix. Okay, so we can see in this animation that the ijth element of A plus B is just the sum of corresponding elements. Scalar multiplication happens when we have a single scalar multiplying an entire matrix or a vector. And the way that we perform scalar multiplication is also element-wise, meaning that that scalar affects every element in that matrix. Mathematically, we might write that the ijth element of alpha m is alpha times the ijth element of m. It's also important to look at what scalar multiplication looks like geometrically. If I have that vector A, again, I can think about that vector as a point. If I multiply it by 2, the resulting vector, 2A, is the vector that points in the same direction as A, but has a length or magnitude that's twice that of A. Similarly, the vector -1/2 A would point in the opposite direction, but have half the length of A. We should also look at vector addition geometrically. And I think the best way to think about vector addition is think about a person walking, and they start at the origin and they first walk the direction and magnitude of A, and from there, from the tip of the vector A, walks the direction and magnitude of the vector B. And then where did they end up? And the result of that question, that resultant, is A plus B. Addition with vectors is still commutative, because you must agree it doesn't matter if I walk in first in the direction and magnitude of B and then A, I will still end up at the same place, corner of this parallelogram. Some nice geometry pops out of that. Now let's combine those ideas of scalar multiplication and addition with a quick example. Here I have 5 data points in space. If I calculate the mean, or the centroid, of this 2-dimensional data, it's called a centroid because I have 2 variables here, x1 and x2. So to get the mean of this multivariate data, meaning more than one variable, I just take the mean of each variable. So this green star here is called the centroid of the data. It can also be called the average or mean, and it's just the point x1 bar, x2 bar. Great. So if I think about these purple points instead as vectors, and also the green star, the centroid, as a vector, what happens when I subtract that mean vector? Well, I simply have to consider walking the direction and magnitude of the purple arrows and then the opposite direction of the mean. Why opposite? Because I'm subtracting. So I'm adding negative the mean. And the resulting points would be centered, which means that the new mean of the data is the origin. This will be a very important fact for us going forward, just this whole idea of centering data, because in every statistics textbook that involves multivariate data, one of the first sentences in the preamble or the introduction tends to be, we assume throughout this textbook that the data is centered. And we will get to see later on why that becomes such a convenient assumption. The last application of scalar multiplication and addition that I want to cover here in this video is that of a linear combination. A linear combination is just a weighted sum. We have these coefficients, the alpha i's, those are scalars. And we could have anything like a matrix or even a number, but typically we'll be looking at a linear combination of vectors, here the vi's. Geometrically, when I take that linear combination, it's very similar to the example we just did with centering data. If I were to take a minus 3b, I would take the vector b, a vector 3 times the length of it, walk in the opposite direction to get a minus 3b. In the next video, we'll get into matrix multiplication.